As we continue our discussion of volume, we're now going to move into some problems. So I've got a big set of directions here, and I will talk about actually solving the integrals, but I really want to concentrate so much on the setup. As I kind of said in the previous video, the setup is really what I'm valuing right here. You can't get too far without understanding the setup, how to draw your picture, where the values are coming from, and then the solving part. At this point, the integrals we get shouldn't be that terrible as far as actually solving them. So I will mention that, and we'll probably solve this first one, but then after that, we'll really just keep focusing on the setup. So, first problem. Well, again, we're setting up integrals that represent the volume of the figure generated by the trapped area revolved around the given axis. So I need to find the trapped area from these curves and revolve it around this given axis. So this is where, again, if you've got a graphing calculator, that can help. But to be honest, we're not going to see super tough problems as far as area. And, most of these are fairly commonly known. And if you've forgotten them, you'll probably get enough practice within the videos and the homework that you will quickly remember them. So, y equals the square root of x is this curve. I typically call it the hook that comes out of the origin. X equals 4 would be a vertical line somewhere over here. I don't need to go crazy with scale, but just to make sure things are to the right and to the left of what they should, that's certainly important. So there's x equals 4, and y equals 0 is the x-axis. As I kind of mentioned, it is so easy for people to reverse and goof these a little bit, and people accidentally make x equals 4 up here and y equals 0 is here. Those are easy ways to make little mistakes, and once your picture is wrong, there's just no way you can keep going forward and get a correct answer. So, the next little point to make, the x and y axis are always here. This time the x-axis was given to us as one of our curves. But there will be other times people think, like, wait, there's two trapped areas, but they're using the x and y axis as boundaries when they shouldn't. So this was given as a boundary, so I will, and that kind of forms this third side. But just to realize as we go along, there's always just one trapped area that we're looking for. So just to be careful with that, okay? So when I do this, I've got my picture, so there's my region, and now we'll shade it in. We're revolving around the x-axis, so I like to put this little revolution symbol, and this flips over. And this really I was honestly trying to basically recreate the bullet that we had in that very, very first generic example. So that's the kind of situation, that's the figure we're looking at, completely solid from top to bottom. Okay, this is my axis of revolution, this is my roundness. So if I want to chop it, which is our only technique, I have to go in this direction. Now, you don't need a different color pen. I just like to because these can get a little messy. So some people really appreciate having the color to show the shading versus the color to show their chopping or slicing. We don't know slicing yet. We'll get to that. That'll be 5.3. But that's your choice. But now that I've got this set up, I already realized it was a solid disc. But if I hadn't, I should definitely realize that now. Again, I like to keep track that the x-axis is running through the middle here. And we know our formula. We're looking at a disc. What is the thickness here? It's the delta x. We're looking at distances in the x direction. And what is my r value? I'm thinking about this formula, the volume of a disc. So I'm looking at pi r squared dx. So I need to find my bounds A and B and what is r in this problem. So which order? Doesn't matter. Those are just the pieces we need. I strongly suggest getting your dx or dy established first. You'll see as we go along, it's easy to make goofs and have the wrong variable here. So make sure you get this first. Because what is r in this problem? Well, just looking at a few discs, R goes from here to here, from here to here, from here to here. So these are different distances, but every single time we're going from the x-axis to a y value on this curve. The y values are the radius, but I need those in terms of x. And that's exactly what the equation does. It's giving me y in terms of x, so that in this first problem, r is just the square root of x. Okay? Now as I start setting up my integral, pi r squared dx, and now thinking about bounds, well, in this one, especially with a good picture, they're pretty much right there. This x coordinate to this one. This one, well, this picture started at the origin. You could technically talk about it's where these two lines are intersecting, but it's just easier to look and say, hey, that's an x coordinate of 0. We'll see a lot of x is 0 here. Not all problems, but it comes up quite a bit. And then what about my rightmost bound? Well, that came from the line x equals 4. That's exactly where this line in the picture came from. So that is my right bound. And there is the setup. Now you could clean that up. And when I solve this one in another 5 seconds, I will. But just to realize, setup, that's what I want to see. That I could see. I mean, again, your picture in this little drawing, that's really to help you. I strongly recommend getting a good picture, understanding how to translate this distance here to this distance here. Those little things will help out. Making sure you have the right variable of integration. All these things are important, but ultimately, that's what I'm looking for. That you have the integral with the correct bounds and the correct values filled in. Correct variable, correct pieces. But now, how do we solve this? So again, setup, you're done. There is the answer. But just a quick reminder, how do we solve an integral? Well, go back and look at the formulas. They all have some aspect of this r squared, and that always makes this piece complicated. But this is one we could simplify by hand. How do you uncomplicate this? How do you simplify it? You square it. The square root of x squared is x. I kick the pi out in front. I've got x dx. Pi pushes along. The anti of x is x squared over 2. Took an antiderivative. That's where I lose my integral sign. That's where I lose the dx. And that's where I get the bounds at the end, the bar with the bounds. Plug in the top, minus plug in the bottom. So I plug in the top, 4 squared is 16, divided by 2 is 8, so I get 8 pi, minus I plug in the bottom, I get 0. And this would have a volume of 8 pi cubic units. Cubic centimeters, cubic inches, cubic feet. We don't have to worry about that part, and we won't. We'll do all of these generically, but just to realize that would have cubic units on it when you're done. Okay, just before I jump into number 2, I just want to point out a couple of quick things about these revolutions. Definitely wanted to get a good problem done, but now to just point out a couple of quick things before we continue with these directions. So, just a quick little point. How do you revolve something like this? If I had that as my starting picture, and you were told to revolve that around the y-axis, you would end up with the exact same thing as if this were your starting picture. So I'm just trying to point this out, that every once in a while, that when you start to look at some of these different figures, you will have figures on both sides of the axis you're revolving around. But if that's true, you'll always have this nice symmetry. So that if this wraps over to here and this wraps over to here, they completely mirror what the other sides are doing. So that's why if you revolve this around the y-axis and then do this, you'd end up with the same shape in both. This one would go to here, this one would go to here, here, this would wrap all the way around, and you'd end up with the same thing. So just to point out, that can happen, okay? But what can't happen? This is not legitimate, okay? It's not that I have stuff on both sides of the axis I'm revolving around. It's not having the symmetry. Because now, what wins? This piece is much bigger than this piece. So as this piece revolves over to here, does it replace this piece? And when this piece comes over to here, does it just get shrunk inside? It's all just garbage. That's not going to happen. So I bring that up here because when you start making your figures, every once in a while you can catch a mistake. If you find two trapped regions, there's got to be some extra information, or you use something a little extra. You should only get one. And then when you actually start to do the revolution part, when you start revolving around an axis, well, again, when you start doing the revolving, something like this can happen. So just a clear little indicator, something went wrong. What went wrong? Well, maybe you were supposed to revolve this around the x-axis, and then that would be perfectly fine. So maybe it was just reading something a little too quick. Again, there's a lot of possibilities, but just to realize something was going wrong if you end up with something like that. Okay, so now, I'm not going to keep recopying the directions, so we're still continuing the setup, but now I want to change a few things up, okay? So number 2, still setting up, but now when I give you your curve, let's start off, let's use y equals x squared plus 1 and y equals, let's go y equals 10. That's it, just those two. We're going to take those two curves and we'll revolve. Let's take this around the y axis. Okay, x squared is our basic parabola, plus 1 just bumps it up 1 unit. So I'd have something like that. And again, I bump that up 1 unit. Y equals 10. Now we're looking at a horizontal line, and we're somewhere up here. So again, notice, I don't need scale. I don't need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't need to go that crazy. Just that line is somewhere up here. Some people, I should have noted this in the previous problems, some people that help make their pictures more effective, they like to keep track of where the curves are in their picture. But plenty of us, we do enough of this. It's like, okay, yeah, that must be that, and that comes from the parabola. So little things like that. So now, and this is what I was talking about, if you now use the y-axis as another boundary, it feels like you have two different pieces of shaded region. But you don't. The y-axis, x equals 0, was not given as one of my curves, so it's just there for reference. So where's the trapped region? It's all of this. So now I've got my trapped region, and now when I take that around the y-axis, this is exactly what we were just talking about. This works. I know my picture's not perfect, but it works because I have that nice symmetry. That these two don't work against each other, that they actually just do the same thing. If you just had this, you'd wrap it around. If you just had this, you wrapped it around. You get the same thing as having both of them. So, well, where do we go from here? Well, now if I'm going to chop this, I'd have to chop in this direction. In this direction, now this would be one edge to the other, and in that direction, it's still solid. It's still a solid disk from one side to the other, so we're still using disk, but now this time, because I had to chop this way, delta y is my thickness. I mean, some people, they're just looking for a way to memorize how do I know delta x versus delta y. It's about the vertical versus horizontal chops. You're always going across your axis of revolution, but it's all about the chops, okay? These horizontal chops lead to these pieces being your thickness, and those are changes in y values. So that's why we're getting delta y. And now, here's the next big thing, everybody. Just a disk, so I just need one R, no multiple R's, just one R. But look at this. how easy it is to go, oh, okay, I see it. The R, center to the edge, center to the edge, center to the edge. People see me doing almost the same thing I did here, center to the edge, and I'm going from the center to the curve. And in this one, center to the curve led to R being the equation. So people say, hey, R equals x squared plus 1. Right track, but still a little off. The reason is here, you're going from here to here. Your R is the x value on the curve, but you need that in terms of y. So what does that really boil down to here? It simply boils down that I need to solve this equation for x in terms of y. We're traditionally more accustomed to getting at y in terms of x, but to force this is delta y as my variable, so I need my r in terms of y. So this was originally given y equals x squared plus 1. So I would have y minus 1 equals x squared, and the square root of that would give me x. Technically, I'd have a plus or minus. The minus is this piece, the plus is this piece. Doesn't matter, you're going to square it on the next line anyway. So in this case, r would be the square root of the entire quantity y minus 1. My integral, pi r squared times the thickness. How about bounds? Y values. So again, the second time that this y became important, I'm not going from here to here, I'm going from here to here. And what is here? Well, we push this curve up 1 unit, so that is a y value of 1. And what is this? Well, that was given as y equals 10. There is your setup. Again, just like the previous one, you want to solve this, still again pretty easy. Squaring the square root to clean this up, and they cancel. Not always quite that lucky, but certainly works nicely here. And then you'd have a simple y minus 1. Anti would be y squared over 2 minus y. And then you'd have your bounds. I'd have the pi kicked out in front, and then would kick it back in at the very end. Okay, so let's keep this going. Let's get a couple more. I don't want to overwhelm you. I want to give you some good practice to get some good examples, but I also want to make sure this video isn't too overwhelming for just our first look at this. Like I said, we have a whole nother technique, and while doing both techniques, we'll just get more practice and understanding with the volume techniques in general, and then we'll have a nice video that sees how it mixes together, and you decide what kind of person you are. So, let's do number 3. And for number 3, I'm going to keep the same curves, but now we're going to revolve for the first time around something that's not the x or y axis. This time, let's revolve around y equals 10. Okay, well, and by the way, this is not the last time we'll see this. When I give you a whole review pack for volume, and we have this come up a lot. Same region, but change the axis of revolution. Sometimes it's a minor difference, sometimes it's a major difference. So we just have to really make sure every time, starting fresh. But what I can do is quickly get this picture put together. And there's our shape. But now I'm revolving around y equals 10. Hey, that curve was already a part of our trapped area. So this was the y equals 10 line. This is the line I'm revolving around. So now, instead of revolving down as we would for the x-axis, we're actually going up to go around this. And we'd end up with again, roundness in this direction as we go around here. So this is actually some sort of like a, I don't know, maybe like an egg or a football. It's not quite pointy enough for a football, but definitely some sort of egg type shape. Okay, well, I revolved around this line, so my roundness is in this direction. So if I want to chop, I have to go across that line. So this time I'll go back to my vertical chops. And now with my vertical chops, from here to here is entirely shaded. So I'm back to a disk. This time it's the y equals 10 going through the middle of that disk. And with this type of a chop, I have delta x. Some people just jump right to dx here. Other people wait until they actually get to the integral. That's fine, whichever way, but you're recognizing which variable you need to have the integral set up with respect to. Okay, so we've got this set up. Again, it's still a disk, so I just need r. But do you see r in this picture? There's a lot of ways to look at it, but to use the original picture before we revolved, r would be here to here, here to here, not here to here, not here to here, not here to here. You got to go from the middle to one extreme. So here to here would be appropriate, but we don't know anything about this curve. So let's go here to here. Let's go back to the original curves that we were given. So this is R. This is R. This is R. Well, how do we get that? We use the pieces we know. We know this is 10. Again, this goes back to why I started with that whole, which way are you measuring and how do you know what the actual distance is? You're already starting to see how that comes up. We're not always just going from the axis to the curve. And by the way, there are some guidebooks I've seen that talk about this, and they don't write the formulas as pi r squared. They write the formula as pi f squared. But that means you have to do so much moving and shifting of your pictures to make that work every time. I think it's a terrible idea. We should see what R is in each picture, embrace R in that sense. That's going to be our better strategy. So again, that's R. Well, if this is 10, and if this is x squared plus 1, both of these, the y value here and the y value here, are giving me their distance above the x-axis. Here the y value is 10, here the y value is x squared plus 1. So what is this in between distance? 10 minus the quantity x squared plus 1. Big total distance minus one piece gives us the resulting piece. And even if you do this with one of the other disks, it's the same thing. This distance is still 10. This distance is x squared plus 1. So 10 minus x squared plus 1. This is 10. This is x squared plus 1. 10 minus x squared plus 1. This is 10. This is x squared plus 1. This 10 minus quantity x squared plus 1. Okay, last piece. So I've got my R. I've got the correct variable, but now my bounds. Previous bounds were not that bad. 1 to 10 were pretty much handed to us in this problem. Sometimes we'll get lucky like that. Other times we're going to have to work harder. In this problem, my bounds are this x to this x. Well, those are not obvious. There is no work here. And again, we're not trying. We're trying to draw these to give us something to visualize, to see where our curves are, to see where our R is. But we're not trying to draw this to scale, to say, oh, that's -2 and +2 or something like that. So we need a better strategy. And what we need to realize is, what's so special about these spots? It's where my original x squared plus 1 curve intersected with the y equals 10 curve. So we're going to have to do a little work to find those points. We'll find those points by seeing where these two curves intersect. And for that, I'll just have to solve a quick equation. This is one, subtract the 10, difference of squares when you factor, that works. Or subtract the 1, solve directly, but just don't forget your plus or minus when you take the square root. And especially now we can look and realize, oh yeah, we did have symmetry. So it did definitely make sense if this is positive 3 over here, that it's negative 3 over here. I mean, there's other ways some people realize, well, if I go from 0 to 3 and double, I would get what would be over here. So there's a few little other ways, but I'm just going to take these bounds, negative 3 to 3, pi quantity 10 minus quantity x squared plus 1 squared dx. Again, a good setup. You're starting to see how solving these can get a little harder. The previous couple, you squared a square root, and the antiderivative was pretty easy after that. Here, we'd have to clean this up. I mean, even right here, some people will 10 minus x squared, distribute becomes a minus 1. That becomes 9 minus x squared. Of course, that's fine. And if you do that simplification here, it makes it a little quicker when you go to square, but don't fall for the easy square the first, square the second. You'd still have to FOIL it out. 9 minus x squared, quantity squared, is not 81 plus x to the fourth. It's 81 minus 18x squared plus x to the fourth. Then you could take your antiderivative. But again, I focused on setup. If you need to know a little bit more about solving, just let me know. But setup, that is perfectly fine. Whether you clean this up or left it the way it is, right technique, right variable with bounds and R value. Okay, last one for today. Problem number 4. Let's take, and for number 4, I'm going to go back to those same curves one more time. Y equals x squared plus 1 and y equals 10. Just taking those two, but this time we're going to go around y equals negative 1. So, now for the third time, I could draw that pretty quickly. If I went around, I want to finish this one up. I don't want to, again, go too crazy with just this first video. So I want to finish with this one. But just think for one moment. If you took this around the x-axis, flipping this across the x-axis, you would have open space. You know what? Let me take 1 minute and show you that, just so we can get a better look at that. So if I took this, went around the x-axis, to realize a common mistake is that people see something like this, flip around the x-axis, and they draw this. And that is not correct. Because you still need to realize symmetry still exists. That when this flips over to here, that you had a gap from this shaded figure to the x-axis. So you're going to need that same gap on the other side. So this flipped around the x-axis, would be something like this. And I know I don't have the prettiest picture here. I could have drawn that a little bit better to show the roundness. And as I showed you when we did our generic washer setup, our figure in that one, in that example, that had some empty space, but was still solid on one side. In this one, if this figure was literally in front of me, I could stick my pen right through the middle of it. I couldn't put my finger or pen through this side or through this side or through this side. It's being wrapped around. This is kind of like maybe like a tire or something like that, or maybe like a fancy flower pot, but it's completely open. Okay, it's got solid on these two sides, but with this gap through the middle, that it presented open space throughout the entire middle. So, if we were going to do this one, and we still only know our chop technique, we'd still have to go about it with chops in this direction. That would be a delta x or a dx inside your integral. And now you'd have the two r's. You'd have the space in the middle, so little r would just be from here to here, or here to here, or here to here. That would be your little r. And then this separately would be your capital R. So in this particular problem, doesn't hurt, I'm already here, so I'm doing this a little bit faster, but capital R would be 10, little r would be x squared minus 1. And that, if you do that too quickly, that looks like, that looks pretty similar to what we did in number 3, but it's very different to have pi 10 squared minus pi x squared minus 1 squared. That is very different than pi 10 minus x squared minus 1, quantity squared. If you solve it, this would also have the same bounds. You'll see you get very, very different areas, volumes, I should say, for very, very different looking and shaped figures. So you see a few similarities. Here, only one r, but it involved the 10 and the x squared plus 1, and we subtracted. Here, I'm sorry, that was a plus 1. Plus 1. Plus 1. All those same pieces are being used, but the order they're put in makes a very, very big difference. Okay, so now, back up to here, and let's finish this up. So, got my initial curve. Y equals -1 will be down here, revolving around that. Even more space. Just point out this little space would give me little space and then I'd flip. But this would give me even more space. So I'd end up having something like this. An even bigger gap in between these two filled in solid chunks. But still so much similarity to what I was just describing and looking at down here, but let's take it nice and slow. So I only have my one technique, so I have to chop this, so I have to go across my axis of revolution. This is not the x-axis, but it still goes the same direction, so I still need these vertical chops. These vertical chops have a whole big empty space in between, whether it's a little empty space or a lot. That is what is leading to a washer setup. And these vertical chops are leading to delta x as my variable. So I really hope, even as we're doing this, just our fourth example, to realize the steps. Get a good picture. Get your filled in region. Do a decent job getting your reflection drawn and think about the three-dimensional way this figure looks. Get your chop, disk or washer, delta x versus delta y. I mean, there's a lot of little organization steps that you could use to make sure you're on track here. Don't have to do all of them in the same order, but it's definitely want to know if you have a disk or a washer and what your variable is before you start thinking about r's and bounds and things like that. Just go back one more time. You know, here I had to do a lot of work for bounds, but I saved that for the end. Here, I didn't have to do any work for bounds, so it was just something I did quickly. So for me, I leave my bounds for the end just because I'm a creature of habit. So I could always get my shape, get my variable, get whatever r's, fill that in, and then however difficult or hard it is to get the bounds, it at least gives me a way so that I don't miss things, that I still stay on track. Okay, so here we are. And now again with our washer, I'm going to need 2 r values. But realize this is our next big lesson. Going around a line that is not the x or y axis always makes things a little more complicated because now that is the center. So just down here, we talked about capital R and little r, and I was going from the x-axis to the y equals 10 curve, or the x-axis to the y equals x squared plus 1 curve. And that wasn't so bad. But now I've got to go from here to those two places. Here to here is capital R. Here to here is capital R. So still use what I know. I still know that this distance is 10, but that's not what I want. I want this distance. But hey, I could easily get this distance. If this distance from the curve to the x-axis is 10, well, the distance from the x-axis to y equals -1 is 1. So that total distance, this time I'll add, and capital R is 11. Now again, a little lucky if this top curve was just a number, but we realize some people look at it as a constant that always has a distance of 10 from the x-axis, which we always just add that extra 1 for the y equals -1 distance. But now the next part, well, very similar. This distance, the y value on the curve gives me this distance, so that's the x squared plus 1, but I need this distance. Same idea. I know what this is. I know this is 1. Add those two pieces together to get that whole piece. So I get x squared plus 1, which that I'll definitely take advantage and just clean up as x squared plus 2. So again, everybody, you see, it's not just a set in stone formula. Again, you need some sense of a picture to work around some of these others, to not just memorize a formula and memorize a way to plug in, but to realize how we use these curves to find the necessary values. Because now we're basically ready to wrap things up. My bounds are still from here to here, so on the x-axis here to here, and that's still -3 and 3. It's the same work I just did a moment ago, everybody, so I'm not going to do it again, right? I just looked at these 2 points are setting up my x endpoints, my left and right bounds, and that's where these 2 intersected, so I set them equal and solved. But now, actually, let me give myself a little more room here. I'm going to be stuck in the corner, so just come down here. So -3 to 3, pi, cap r squared, minus pi, little r squared dx. There's a setup. That is all we're looking for. And one more time, thinking about the solution, if you actually solve this integral, take the pi out of both, make your life easy. Gotta square both of these. That's a quick 121. Here again, you gotta FOIL, you gotta distribute a negative. So there's still good little steps to remember about solving integrals, but you shouldn't need any u-subs at this point. Maybe there'll be a random one at the end of a homework section, but most of these are just pretty direct. Clean up the squares, get your antiderivative, and then plug in your bounds.